On. There it is. I guess it is on. Do we have a pointer up here? I just apparently completely and totally unprepared.
Okay, is that one? Is that just
No, it's a pen.
I have one. Inside this box?
Oh, inside the box that holds a pointer in there? Yeah, that'll do.
Do you want to click?
No, that'll be fine. I'm not going to be moving around a whole bunch, it turns out. Yeah, there's a pointer. All right. Okay, well, first I'd like to thank the organizers and ITAMP for hosting me here. It's been a good workshop for me. I'm very new to this sort of area. I'm, simple few-body theorist from, the backwoods of Maryland. So I've learned a lot, and I'm, kind of happy to see what's happening in the field. So this is some work that I've been doing for the last little bit here. I started actually at my previous institution, Western Washington University, but I've been at the US Naval Academy for the last year. Before I get into anything, I want to just thank all the collaborators I've gotten to work with back at my former institution, Western Washington University. Brad Johnson had a lot of background in quantum Hall physics, so he was a good resource for helping me starting with this. Jose Dincao at GILA has been doing some numerical calculations using Leonard-Jones potentials and that I'll just mention briefly at the end. We are continuing some of this work. And then my former student back at Western, who actually did a large portion of this, I was really impressed. He was an undergraduate at the time, and we lost him to math over at the University of Oregon. I tried so hard to convince him, but he wanted to do math. So just a quick outline, very sketchy outline. Wow, I really need to move that away, don't I? Let's try. Down there. Okay, that's hopefully a bit better. This talk will probably be a bit shorter than the ones you've seen. I don't know how long I'm going to be able to just stand up here and yammer at you. So I'm just first going to if you were here for Rachel's talk on Monday, you saw some of this, but I'm going to reintroduce what the adiabatic hyperspherical method is and hyperspherical coordinates in general, and how I can apply them to this work. Then I'm going to talk about how we can include interactions. Specifically, I'm going to largely talk about contact interactions, zero-range interactions for the three-boson problem, but also talk a little bit about some longer-range interactions and how they sort of affect the adiabatic potentials and what kind of energy levels we get out. And then finally, I'll just have a thing about just looking at the very lowest energy state for three bodies as a function of angular momentum. So why don't I get into it? So first, I just want to talk about hyperspherical coordinates. And this is going to be really brief. I like to say the first step for easy few-body scattering. I should probably put easy in some quotes there. But generally, what we're going to do here is we're going to treat the hyperradius, which is this coordinate that is really the sum of the squares of the particle separations, right, as an adiabatic coordinate. In other words, we're going to freeze that coordinate and solve the Schrodinger equation and all the remaining degrees of freedom. And what we've done here is we've absorbed all the length scales of the problem into a single radius, and everything else is going to be described as angles. You can think of this hyperradius as sort of the RMS size of my system. So I have just here's my three particles in 2D. Conveniently, I can actually draw that. That was a bit of a joke. It's okay, all right. And you can kind of just think about the RMS size of that three-body system as my hyperradius. And it really gives us a very convenient view of the energy landscape if we're dealing with particles in free space. And the reason for that is, we freeze a hyperradius, solve the remaining angular degrees of freedom. First, because all the length scales are set into this hyperradius and we're freezing the RMS size, it sort of acts like a bound system. So we can, the Born-Oppenheimer kind of approximation is great because we get this infinite set of our energies at that hyperradius. And then we change the hyperradius, do it again and again and again, and you paste them all together and you get your kind of Born-Oppenheimer potentials. But the nice thing about that is we've sort of taken all of our continuum behavior. Like if you have three particles, you have, even if you've removed center of mass, you have sort of two continua. We have a continua like the separation in between two particles, and like the continuum of the third particle's distance from those two. That's sort of two continua in there. But we've taken both of those continua and sort of put them together into one, the continuum of the hyperradius. So that's sort of convenient for us. And when we do this sort of behavior, we can get a lot of ideas about what's happening in the system just by looking at the behavior of the potentials. For instance, the threshold behavior. So what I'm showing you here is the energy landscape for three bosons in 2D interacting via contact interactions. This is for zero angular momentum. Right? And some of the things you can pick out here is, for instance, you can look at this lowest potential curve here. And that's going off actually to a negative value, which means that when I go out to infinity here, I'm at some negative energies. And if you actually map it out, that's exactly the energy of a dimer bound state. So what this potential corresponds to is a dimer with a free atom far away from it. So this is an atom-dimer potential here. Then we have this series of potentials, and there's an infinite series of them actually, all converging down to zero energy. And so what these potentials correspond to is potentials that go off to the full three-body continuum. All three particles are very far away from each other. And so if we have all these potentials and the couplings between them, we can do interesting things, like saying what happens if a system comes in along, say, this lowest three-body potential curve and transitions to this lower atom-dimer potential and then leaves. So we have this sort of process. And if we have those couplings, we can actually get rates for that sort of scattering process. And what we found is this idea of recombination, where we have three free particles come in, an atom and a dimer come out with extra kinetic energy later. We can describe these sort of processes. That's why we like hyperspherical coordinates for a lot of these sort of few-body scattering processes. Another reason, when you're dealing with short-range interactions, if you have in free space, when the hyperradius is much different than any of the other length scales within the problem, you tend to get potentials that have a nice universal form, this sort of 1 over r squared potential form. Because if r is your only length scale, because it's much different than any other length scale, then h bar squared over 2 mu r squared, where mu is sort of an effective n-body effective mass, this is your only energy scale. So these are your only sort of potentials when you're at disparate length scales. Right? And for instance, if this was a full free space behavior and all three particles were very, very far apart, and lambda here was an integer, this would be the potentials for three particles in free space. Right? Kind of sort of the equivalent in higher dimensions of your centripetal barrier in spherical coordinates. Right? Of course, if you have different length scale discrepancies, you can get into regions where this lambda is no longer necessarily an integer. It can be complex, and then even in certain cases, it can even go to complex values where the square of this goes negative. Lots of interesting stuff inside there. But everything we need to know about the system then is sort of all tied up inside what's happening with this stuff on top of the r squared. So the reason that that's why hyperspherical coordinates are useful in free space scattering problems, but we're not in free space here. We're going to have a magnetic field in 2D. So why is that useful? Well, why don't we just look at what happens when we have n particles in a magnetic field in 2D? So here's our Hamiltonian. We've seen it the last 3 days infinite times, it almost seemed like. If we had an extra interaction in here, I like to call it the Hamiltonian that's launched 1,000 dissertations. Right? But it's well known. So in this work, I'm going to work in the symmetric gauge, where I'm just going to have a constant magnetic field. And in fact, I'm just going to kind of wrap the Q over C business here into a single coupling constant, because I'm not going to be dealing with real actual charged particles. They're going to be some sort of fictitious particles or atoms in an artificial gauge field, or really whatever I need to wave my hands around it on a paper to get them to accept it. Right? So when we put this all together, it turns out, or expand all this stuff out, we can do a little rearranging. We can separate it out into a center of mass Hamiltonian, which is exactly what we'd expect to see for a center of mass. Single particles, with weight big M, where M is the total mass of the system, going around in Landau levels. And then we can get what I call the internal Hamiltonian, which is just the Hamiltonian after we've removed that center of mass. If we rearrange this into a clever way, this is the sort of form of the interaction, where this Laplacian sub d is actually a d-dimensional Laplacian, where d is now the total dimension of our system, 2n, minus the 2 degrees of freedom that are inside the center of mass. So this is our sort of internal dimensions of the problem. Just something to point out real quick. It should look really familiar. We have now a d-dimensional isotropic oscillator in hyperspherical coordinates, which is really easy to take care of. We can do all that. And then just a nice, the normal angular momentum shift. But I'll point out this is the total internal angular momentum of the system, how fast the system is spinning around. Anyway, and so I'll also point out here that I've chosen my magnetic field to be pointing in the negative z direction, so I can deal with positive values of m. I don't know, everyone throws around negative m's, and I always have trouble remembering minus signs, so I set this up so I can always deal with positive values of m whenever I want to. So if I diagonalize this Hamiltonian, I can get the energy spectrum, and it looks really quite familiar, right? So here's my oscillator spectrum, my lambda level spectrum that comes out of this. And what I find is I get an n value, which corresponds to the hyperradial quantum number, the number of hyperradial nodes in my solution. And then I get lambda minus m over d. Some caveats on lambda. Lambda is the grand canonical angular momentum quantum number, sort of the higher dimensional version of our beloved L, right? M is the total 2D angular momentum, z projection of my system. And d, as I said, is just the number of dimensions in the system. And then there's this over 2. So some things to point out here. Lambda has to be, if I break up my system into Jacobi coordinates, so n minus 1 Jacobi coordinates for my entire internal degrees of freedom, right? Each one of those Jacobi coordinates can have an angular momentum associated with them, a little m, and lambda, my hyperangular momentum quantum number, has to be greater than or equal to the absolute value of the sum of, or the sum of the absolute value of all those angular momenta. So there's a lower bound on what my hyperangular momentum can be, and I'll just also mention that big M, my total angular momentum, is of course just the sum of all the angular momentum. But what that means is for positive m, if I go to my smallest possible value of lambda, lambda is exactly equal to m. So if I go up to here and see my lambda is equal to m for my smallest possible lambda, these cancel out. And of course, what I get is the lowest lambda level. Landau level, lambda, there's a lot of them. So the lowest Landau level. So the lowest Landau level in this picture corresponds to a system with no hyperradial nodes that lives in the lowest free space hyperangular behavior, right? And it's, of course, infinitely degenerate. So each value of m that I choose, I can have a value of lambda for that, and it just goes on and on and on. And so this is sort of our Landau level picture that we can put together in hyperspherical coordinates. And we can look at, say, transitions between different Landau levels in two different ways. Right? Now, because we're in this hyperspherical picture, our coordinates are collective coordinates, intrinsically a collective coordinate. The hyperradius is a breathing sort of coordinate where we have a change in the RMS radius behavior of the system. And then the angular coordinates correspond to configurational behavior, so how the atoms or these particles are together inside the state. So there's two different ways I can make transitions between Landau levels. I can just go straight up by incrementing my hyperradial quantum number, which is sort of a breathing mode excitation, or I can sort of make these sort of diagonal transitions where I make a change in lambda, the hyperangular behavior, right? And that's a configurational change between these different things. So there's two different sort of collective coordinates that we can do. I could also like go change increment m to negative m or things like this and go up that way, but I'm only going to deal with positive values of big M for now because that's the way I want to deal with it. Okay, so that's why one of the things that drew at me to trying to attack this problem with hyperspherical coordinates. First, we already have some really nice tools built up for hyperspherical coordinates in the few-body realm. Also, the in-field problem has such a perfectly separable, nice interpretation that can come along with hyperspherical coordinates. So, wanted to see how these things go together. So we can just look at the whole Schrodinger equation with everything written out in all its glory. So these two terms out in front here are actually that d-dimensional Laplacian. Here's our hyperradial derivative terms. We're going to kind of ignore those for a little bit. And then we have our hyperangular pieces of that Laplacian. So we have this big lambda squared, which is there. Then we have all the interactions. I've included my interactions here. And then I've got my oscillator term, which comes from the magnetic field. I should mention that omega c here is, of course, the cyclotron frequency, and my angular momentum shift. And I just want to point out that the only place where the magnetic field shows up in this Hamiltonian is inside these two terms. But in hyperspherical coordinates, those things are really easy to deal with. We fix our total angular momentum m. R is already a fixed thing if we're dealing with the adiabatic hyperradial. So these things kind of come along for free in hyperspherical coordinates. The magnetic field is completely free. The other thing I'm going to point out is, okay, I guess maybe this was out of order. I just will point out this is the grand angular momentum operator, this lambda squared. It's the analogy of the angular momentum operator in 3D, just more angles involved. Okay. But the thing I want to point out is for a fixed total angular momentum, all of our angular dependence, these hyperangles, once we've removed the hyperradius or froze the hyperradius, lives inside just these two terms, if I have a fixed m. But even better yet, these two terms are exactly the same two terms you would see for free space without a magnetic field. So if you can solve the 2D few body problem for n particles in free space, you can do it in a magnetic field for free. It comes along for the ride. All you have to do is solve this problem. I say all as if it's somehow pretty easy. So our goal now is to do this Born-Oppenheimer thing. In other words, I want to try and solve this adiabatic Schrodinger equation, right? Where I'm going to fix the hyperradius. That's why this thing has a little semicolon there. Fix the hyperradius, and then I'm going to solve this partial differential equation in the remaining angular degrees of freedom. When I do that, what I'll find is a set of potentials, adiabatic potentials, that are functions of R. Right? And if I can rewrite these adiabatic potentials in our kind of telling way, this 1 over r squared way. I think I'm probably missing an h bar squared in there, but what's a factor of h bar? All right. We'll have this. So this sort of convenient form is nice because now we've isolated to just this 1 over r squared behavior. This, if we can find out what this thing does, and it can be a function of r, then we basically know everything we want to know about this problem. And we can do that overall. So that's the picture, the adiabatic picture that we're going for. Now to be able to solve that, we actually have to have some interactions to put in there, because now we're actually in the nitty-gritty. I need to know what problem I'm actually solving here. Right? So the thing that kind of originally got me interested in this system was this 1983 paper from Gervin and Jacques, which I'm assuming most, if not all, the audience members know of. It's a great paper. It's one of the early papers where starting to look at few particle states in magnetic fields with Coulomb interactions and trying to extract some of the behaviors in there. And some of the behaviors I thought that took me a while to understand, wasn't intuitive to me, so we have these cluster states. First, that there's a bound state in a magnetic field. It didn't make sense to me, but now I have a little bit more of a grip on that. But also the fact that things get lower in energy for higher angular momentum. It doesn't make any sense to me, but I guess it does now, because if something's spinning a bit faster, the particles are further apart. Lower interaction energy, the lower interaction energy beats, or because all the Landau levels are flat, sort of if we can lower the interaction energy, we can lower the overall energy. So this is all well known. But the thing that really I found striking here, and people talked about for a while as far as I can tell, is these magic number things. So like, if you look at this, instead of having a nice smooth decrease in energy for 3, 4, or 5 particles as a function of angular momentum, it's sort of dippy, right? And for 3 particles, we can go 1, 2, 3. We have an anomalously low energy, and then it doesn't go down anymore, and then 1, 2, 3, 1, 2, 3. So for 3 particles, every third angular momentum state is a little bit low. For 4 particles, it's every fourth. For 5 particles, it's every fifth. If you go up to 6 particles, it starts getting a little bit muddy and is not as easy to see. But this is the thing that we are kind of interested in. And we had this sort of new approach, this hyperspherical approach, which is sort of a geometric interpretation. So we thought maybe we'd be able to shed some light on that. That was our original goal. So the first thing we started doing was, well, this is all lowest Landau level calculation. So we decided to do a lowest Landau calculation within the hyperspherical picture for, instead of just 1 over r interactions, Coulomb interactions, what if we had a 1 over r the alpha kind of interaction? What does this thing go like? So we just do a lowest Landau level calculation. And in truth, what we do here is we solve the hyperangular Schrodinger equation, freezing that lambda value to the lowest Landau level lambda, and then we allow the hyperradial behavior to be whatever it needs to be to best solve this. So it's sort of we are mixing in some higher Landau level stuff in there, but not a lot. But this is what we see. So what's happening here is, as alpha increases, we're going down in the stream. For alpha equals 0.1, so basically a flat interaction, not too surprisingly, it's just almost a constant shift that is introduced by the interaction. But as alpha gets larger and larger and larger, in other words, the interaction starts getting shorter and shorter range, this sort of deviation, the dipping behavior in the magic numbers, right, gets more and more pronounced. So when we get down to here, alpha equals 1.3, we can go all the way out to alpha equals 2 with this method. We can't go beyond alpha equals 2, though, because things blow up real good at us. And, right? But as we keep on going down, this dip, this magic number behavior, it starts becoming more and more and more pronounced. So that led us to think, shorter range interactions enhances the magic number behavior. Well, what's the shortest range interaction I can think of? It's a contact interaction. So maybe we wanted to examine this sort of magic number behavior in the context of a contact interaction. So this is the contact interaction we chose. We didn't just do a straightforward delta function, because delta functions in 2D, if you really take it seriously and try and diagonalize without doing some fancy footwork, blow up at you. So this is what we chose. And to point out, and it's this regularized contact interaction we got from Congelon and Bloom's work in 2006. It's the same contact interaction I used to show those potentials from the very beginning of this. There's a few things to show up. First, it is in fact zero range. I have my delta function here. We have a bunch of terms, this logarithmic term on the diameter and these derivative terms. And really what that all this gobbledygook does is it really just enforces a short range boundary condition on it. So if I use this thing in a Lippmann-Schwinger equation or in any sort of serious way, all that we are really doing with this contact interaction is enforcing a boundary condition and basically creating a connection between the regular and irregular parts of a scattering wave function. That's sort of symbolized by, and that sort of connection, it comes through as this 2D scattering length. And so really our parameter here for this interaction is the 2D scattering length. And all we care about here is I can just wave my hands around it. It's going to the 2D scattering length determines the strength of the interaction. The scattering length is always positive in 2D. For a very, very large scattering length, when A is much larger than any of the length scales in the problem, that will correspond to weakly attractive interactions. Very small scattering length, much smaller than any of the other length scales in the problem, it's a weakly repulsive interaction. So that's what our contact interaction looks like. There's some other features of this that will become apparent in a little bit. This is what we want to do. So we can actually use this, apply our boundary conditions for the three-boson problem. You can go ahead and do that. Point out, of course, that this is clearly I'm not even talking about fermions anymore, because if I have a contact interactions, fermions don't care about contact interactions, so I'm not talking about bosons. So I've left the land of electrons entirely. I had already left the Coulomb interaction, so why not throw away the fermion as well? So it turns out that we can very nearly analytically solve for these epsilon coefficients in our potentials for this contact interaction in 2D for three-particle problems. It comes down to just root finding on this lovely transcendental equation that you don't even need to pay any attention to. It just took me a little while to derive it, so I feel kind of good about myself, so I thought I'd show it. I mean, it got some polygamma functions and some hypergeometrics in there. It's pretty fancy, right? But we can find these epsilons, and they are in fact a function of R. If we put those into these potentials, the types of potentials we start seeing look like this. So this is again just the m equals 0 behavior, right? So now I've included the trap in these potentials and that angular momentum dependent shift, though m equals 0 here, so there's no shift at all. And these are the kinds of potentials we see. And so in this figure, I'm showing 3 sets of potentials for the solid curves correspond to a very small scattering length. A is much smaller than the radius. The dash curve is a intermediate, that it's a fairly small or intermediate one, and then the dotted curve is a very, very large scattering length. And what do I mean by small, medium, and large? I mean in comparison to this sort of magnetic length, which is the oscillator length that's associated with the cyclotron frequency. Right? So that's what I mean by large, medium, and small. And there's some neat things that go on. So one thing I haven't talked about is we can also effectively, nearly analytically, up to some root finding, get the couplings between these potentials. So all I'm showing you here is that we can actually just solve this whole problem. And in the inset here, I'm showing the very large scattering length potentials, which are the dotted curves here. I'm showing the large scattering length potentials on a very different scale, just to emphasize this sort of trapping behavior that is introduced by the magnetic field. So these are the things that we're trying to solve. And once we have these potentials and we have the couplings between them, we shove it into our favorite 1D coupled partial coupled differential equation solver and get our full spectrum out. So this is what the full spectrum looks like. There's a lot going on here. It's hard to see any of the colors. The red looks very black on this. But you can see a few features. For instance, you can see as the scattering length, so this is scattering length over the magnetic length. As the scattering length gets really, really small, right, we get this series of states, these energy states that are all diving down really fast. And that's true for any value of m. We get this set of states that are going down. But on their way down, these states go through a series of very narrow avoided crossings. And what are these avoided crossings? So whenever you see an avoided crossing, you should think about what diabatic states are going through here. Right? If you look at the states that are going through, that's the dash line. These dash lines correspond to just the energies you get out if you ignored any of the couplings between the potentials. So just to say what these things falling off into the middle of nowhere are, that's actually the fact that we have a dimer bound state that's showing up with this contact interaction. And that dimer bound state has a binding energy that goes like 1 over a squared. So as a gets small, that dimer binding goes off the charts. So these things correspond to things that look like kind of atom dimer states in a field. We're not going to be really concerned with those. We're going to be concerned with the kind of behavior, all the stuff happening up here near the Landau levels. Right? Another thing that we learned from all this is that all these couplings are fairly narrow. They're not especially broad. And so unless you're right on a scattering length, right at where a state you're concerned with is going through one of these crossings, you can largely just ignore these couplings between the different potentials. We can throw away that. We can just treat this as, solving one-dimensional, single-channel scattering problems each and every time, which makes our jobs much easier. In other words, we found a very nearly separable system in this. The three-body problem in a magnetic field with contact interactions is very nearly separable in hyperspherical coordinates. That's kind of a convenient thing, right? So we can go to this separated thing, we ignore the couplings, and we get a very nice picture of what's going on. We get for each m, we get the series of states that are all attached to the lowest potential in this thing. And as the scattering length gets smaller, that lowest potential falls off the map because it corresponds to a dimer, so it goes down like 1 over a squared. And that's what all these black or solid black curves correspond to. There's states that are falling down, following that 1 over a squared, but then they're still in an oscillator potential, so we get a stack of states associated. The next set of states we get here are these dashed red ones. Those are the states that correspond to the lowest three-body state that has no dimer-like potential in the small scattering length limit. We can see some neat stuff, like as I go from small scattering length to large scattering length, right, they get swept from the lowest Landau level up 2 for m equals 0. Right? Up 2 for m equals 2, and we start at the second Landau level for m equals 1, and they get swept up. So as I go from small to large, these states get swept from one Landau level, non-interacting state or behavior, up to the next non-interacting behavior. So this is the picture that shows up. So we have, basically all the information we could ever want. So we now have all our states, we have our potentials. Let's start playing around with just the lowest energy state. And we're going to actually focus on small scattering length for now. So small scattering length, as I said before, corresponds to weakly repulsive interactions. Right? So what happens when we have a weakly repulsive interaction for this three-body system? So I can do that, and in fact, I can just show you what the lowest energy state near the lowest Landau level, that's what this corresponds to, the lowest Landau level, looks like as a function of A. As you can see, as I go from very small scattering length, it's just slightly perturbed up, that's weakly repulsive. Then I go into this sort of strongly interacting regime in the intermediate A region. It gets pushed up, and then from down below I get a new set of states that come up that are weakly repelled, or weakly attracted, right, as I go to very, very large scattering length. So here's our weakly attractive region, here's our weakly repulsive region, and here's the sort of transition in between the two. Okay. So if I examine these states, I can say each one of these corresponds to a different value of the angular momentum, right? The total angular momentum of the system. Right? This top curve here, which is actually the highest energy state, corresponds to m equals 0. Okay, that's nice. We already knew we start out at high energy, and then as angular momentum increases for repulsive interactions, we go down in energy. Okay, so then interesting thing here for me, it took a while to figure that out. There's no m equals 1 state, but then there's an m equals 2, which is lower in energy than m equals 0. Okay, everything's going along fine until you see the m equals 3 state, which is way down here. Then there's an m equals 4 up here, and m equals 5. There's this weird sort of pattern as a function of the angular momentum. Right? And we can just isolate a single scattering length. The energy is at a single scattering length. I'm going to choose 0.1 times the magnetic length here. And this is the sort of behavior that we end up getting. Okay? For a weakly repulsive interaction, we end up with this very, m equals 0 is pretty high. Here's the inset, just shows everything. M equals 0 is pretty high. M equals 1 gets shot up off the charts. But then after that, we have this sort of even-odd oscillation in the total energy of my three-body or my three-boson system. Okay, well, maybe that's sort of just a parity argument. Yeah? Oh, fine. Okay. Right? Okay. All right, so there's some questions that come up here. So first, what is up with M equals 1? It's way off the charts. Another thing that's somewhat interesting is that for this three-body system, M equals 3 seems to be universally the lowest energy state. It's not that it keeps on going down with higher angular momentum. It's M equals 3, lowest energy state. It's bizarre. Couldn't quite figure out what was up with that. And also, at very large M, it's not just going down to the lowest Landau level, which would be way down here at 1 in these units, right? It's going to some finite value for high angular momentum. Why isn't it going to some sort of non-interacting level at very large angular momentum? So the answer to that came in when actually Chris's and Rachel's paper came out on degeneracy. We started looking at the degeneracy of the lowest Landau level for 3 particles. And this is the sort of degeneracy behavior you find for 3 particles as a function of M, for 3 bosons, right? There's a single state for M equals 0. Turns out there's no states for M equals 1. You can't maintain bosonic symmetry with 1 unit of angular momentum internally here. We're removing center of mass behavior. And then there's 1, 1, 1. And then you get these weird extraneous jumps in the degeneracy before it goes back down for 1 and then back up. And then it follows this very nice regular pattern for 3 particles. Right? So what's happening here? Yeah, I just said that. Okay. So what's happening here? Well, remember what happened here is that I had an interaction that explicitly chose out, projected onto states that had an M equals 0 interparticle component. That's how I had this interaction. That's what that derivative term did in my pseudopotential. I projected onto things that had the right boundary condition. And it turns out for 3 particles, for 3 bosons, for each value of the total angular momentum, there is at most 1 state where you have non-zero or some zero component of the interparticle angular momentum. Right? So in this picture, whenever you have a lowest Landau level, I should say at most 1 lowest Landau level state with 0 interparticle angular momentum, whenever you go to a place where you have more than 1 state in your lowest Landau level, that means you have states that have no zero interparticle angular momentum. And in fact, if you examine at these different values of M where you have these anomalous degeneracies, those correspond to exactly introducing a Laughlin state. So this new state is a Laughlin state. We have a Laughlin state, and then we have a state with 0 interparticle angular momentum. Then we have 2 states, one of which has a 0 interparticle angular momentum, one has some sort of Laughlin behavior with probably some other stuff, and then I have a new Laughlin state that gets introduced, so on and so forth. But remember, whenever I have more than 1 state, I have it in my lowest Landau level. That means I have at least 1 state that has no zero interparticle angular momentum, which means by an S-wave interaction, it's a non-interacting state. So if I actually was to be honest about what the energies for this small scattering length 3-body system look like, is I have an M equals 0 state, then M equals 1 gets shot up off the map because there's no lowest Landau level state. I go up to above the 2nd Landau level. Right? Then M equals 2 is up here, and then M equals 3 is lower, M equals 4 is down here, M equals 5 is here. But then when I introduce a Laughlin state, all of a sudden I have a non-interacting state, so that's at 0. M equals 7, no Laughlin state, still only 1 state, it's up here. Then M equals 8 and beyond, I'll always have a non-interacting state sitting around. So this is the more honest picture of what the energies of this stuff look like. After M equals 7, and at M equals 6, we have a set of states that are non-interacting, just living down here at the lowest Landau level. Right? And we can actually do the full finite range calculation, which includes all higher partial waves and do everything. This is what Jose has been working on. And this is what it is. So the x's are the zero range calculation, and the dots and lines correspond to the finite range calculation. And what we're using here is a Leonard-Jones potential, a 612 potential with a van der Waals length that is a tenth, with a scattering length that is 1,000 times the van der Waals length, but still in the small scattering length regime with respect to the magnetic length. So this is a large, small scattering length. Okay. But if we go into this regime, what we see is really an excellent agreement with the zero range calculation for these states that have a 0 interparticle angular momentum component. But we're also picking up all these extra states down here that live at the lowest Landau level that are non-interacting, or very nearly non-interacting in this regime. So this is what happens when we're in this specific limit. But I have a question. What happens if I didn't have very weak higher partial wave interaction? Right? What if I had like a strong D wave interaction as well as my S wave interaction? an m equals 2 interaction. Well, this is just a schematic of what I would expect to happen. Well, for these lower states, basically everything is going to be dominated by the S-wave interaction still. Right? And we follow the same sort of pattern as we saw before. But then as soon as I hit these states where I have a higher, or my degeneracy gets higher, that non-interacting state will all of a sudden get kicked up because it has a D-wave interaction involved now. So it's no longer going to be just at the lowest lambda level if I had a strong D-wave interaction. Right? So this is the sort of behavior that I expect to see, that I'd have this set of S-wave interaction dominated states, and then this set of D-wave interaction dominated states, and then probably SPDF, G. A set of G-wave interaction dominated states here, each one getting lower and lower and lower because at higher partial wave expect weaker interactions. Right? So this pattern of when these things show up will just be determined entirely by the degeneracy pattern. But then if I just look at what's happening here, I can just trace what is happening to the absolute lowest energy here. I have a low energy state, then I have 1, 2, 3 low energy state, 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 on and on and on. That's our magic numbers popping out. So what we're sort of surmising here is that the emergence of these magic numbers in the low cluster numbers, the 3, 4, 5 particle states, is actually just sort of like a anti-aliasing, a combination of the degeneracy patterns that are showing up within the lowest lambda level and this sort of even-odd parity oscillation. Looking at 4 particle states, we found that if we just make this assumption that goes through even-odd parity oscillations and put it on top of a degeneracy pattern in the same way, it does appear like it probably will have this sort of magic number behavior. The degeneracies are a bit harder or nastier to deal with 4 particles because it's hard to figure out when you have S-wave interactions and when you have this new non-S-wave sort of states showing up. Right, well, it's not hard. It's just a little bit more of a pain. Right? So with that, I'm just going to summarize. So we might see that we need to see, we're hoping that this magic number behavior, or we see that the magic number behavior is enhanced by short-range interactions. This contact interactions resulted in an even-odd parity oscillation, not magic number behavior, which didn't make much sense to us at all. But then when we include the degeneracy at the lowest lambda level and actually include the full set of states, this magic number, or the parity oscillation with the degeneracy pattern sort of seems to show some magic numbers. And we're working now on actually including some of these strongly interacting D-wave potentials, as well as we're going to fermions as well with the finite range interactions, looking at like a P-wave resonance or things like this. So with that, all right, and if you're interested, we have a paper on the contact interaction stuff that came out a little while ago. With that, I'll welcome any questions.
So just remind me, the Durbin-Jack paper about the Coulomb interacting fermions in a harmonic
Yeah.
kind of in the quantum Hall regime. So I used to hang out with people doing quantum dots, and they were studying these kind of things. And that's a regime where the particles are localized and they form what's called Wigner molecules. And so if you have 3 particles, they have like a triangular shape, and if you have 4, they're quadratic.
If you go in.
I don't remember if the transition is at 5 or 6, but at some point you no longer have a ring, but you start to put one in the middle, and then you have concentric rings, which is probably why your magic numbers get more shady at that point. And I also remember people discussing symmetry, like group theory-based arguments for why, if you have, say, a triangular shape, why you should have a dip in energy and this triangular momentum. So it's been discussed from that.
Yeah, we looked into the symmetry arguments. We didn't find anything that was especially convincing other than saying triangles happen, and it's nice. But I mean, we see triangular behavior with the Coulomb interaction, but when you go to the contact interaction, some of those triangular symmetries sort of start disappearing. It's not as clear. You start seeing like lattices of triangles showing up as nicely. The Coulomb interaction is sort of like, that long-range repulsive interaction sort of kindly, or not kindly, it's very nasty, but does tend to put everything into these sort of highly symmetric pictures. The contact interaction is not quite as clear, but we're still seeing some of this magic number behavior showing up. So we think that there's probably something more than just the symmetry argument going on there.
Could you remind me, I think there is no Thomas collapse in this 2D system?
In the 2D system, no, there's not. There is actually always a short-range barrier, and that happens because when you go to very small hyperradius, the interaction goes back to non-interacting. And if you go to very large hyperradius, it goes back to non-interacting. It's the scale comparison to the scattering length, and I didn't talk about it much, but when you have in that contact interaction, very large scattering length is non-interacting, and very small scattering length is non-interacting. So it sort of transitions from one to the other.
The other question I had is this logarithm term really so important if you had just used a contact interaction, but do what people usually do when they use it and make sure you don't actually try to push it to exact convergence. Wouldn't it give a pretty similar story?
For the weak interactions, it certainly would. We want to go into the get up to unitarity and really push this to the stronger interactions. But yeah, it should, for weak interactions, just put in, repulsive contact interaction should look pretty similar. But then I wouldn't have gotten to show my transcendental equation, and really, that's what was half the point of the talk.
And so you don't ever need a three-body parameter in 2D?
It depends on who you talk to. The effective range actually has a logarithmic behavior in it as well, so it tend to get very, very large, which means that this sort of a picture really isn't very good for those short-range interactions. So you do need some corrections on that. I don't know if it's 100% clear whether or not a three-body term would make a huge difference on that, but you don't need a three-body term to stabilize it.
Okay, no other questions? Let's thank Seth again.